Thank you, Mr. Chairman. Good afternoon. The work I'm going to present you today has been carried out in cooperation in the University of Trenton, University of Manchester, and Oklahoma State University. The focus of my presentation will be the practical behavior of short-peened notched specimen. In particular, we want to look at the effect of residual stress ahead of the notch. Short-peening is a very effective surface treatment to improve fatigue resistance of aluminum alloy. It enhances the fatigue resistance, but also reduce the fatigue data scatter and improve the reliability in the fatigue design, and reduce also the fatigue notch sensitivity. Obviously, you have to account also for the surface morphology worsening and also for the manufacturing. One open issue that we have to further investigate is how to incorporate residual stress in a fatigue design criteria. In particular, we would like to study the residual stress evolution during the service in service lives, and the residual stress field in the vicinity of complex geometrical details, because in any component we have complex details that can influence the onset of residual stress. In the past, we studied the reverse bending fatigue of aluminum 7075 alloy by carrying out a reverse bending test, and we observed stress relaxation during cyclic loading. And we found a good representation of fatigue results by incorporating the stabilized residual stress as mean stress in a multi-axial fatigue criteria. In order to take account of the notch sensitivity, we use a line method based on the definition of a critical length. What we do in this case to model the residual stress, which were measured by XRD analysis, and we introduced in a finite element model the residual stress, but considers only the frontal surface of the specimen. What we have found in terms of results are quite, the reproduction of fatigue results are quite good. Is quite good, and we also can observe the fatigue stress relaxation during as a function of the applied stress. What happened in this case? Yielding in the compressive part of the cycle is the main point that dictates the fatigue property of this material. In particular, it can explain the stress relaxation and also the fatigue behavior. We want now to enlarge our analysis, and I come to the objective of this research. We want to extend the analysis of our research to the very high fatigue, cycle fatigue regime up to 100 million cycles, in order to investigate how effective are short-peening in this very high fatigue life regime. Moreover, we want also to study how notch root can influence the onset of residual stress due to short-peening. And so we carry out some experimental measurement in the region of the notch. And finally, we want to try to investigate not reverse bending fatigue, but pulsating bending fatigue, bending load, in order to avoid the compressive yielding of material and to avoid this effect that can dictate the behavior of material. So, experimentation has been carried out on the same alloy, and we consider three different three different notches, blue notches, with stress concentration factor ranging between 1.5 to 3.7. Short-peening was carried out following the parameters that are reported in this table. In particular, we performed a gentle alloy intensity short-peening, which is the most effective to improve fatigue resistance of aluminum alloy. You can see the same analysis of the surface. We can observe a complete surface coverage and also a material flow at the notch edge, which are rounding of the notch edge. As I said before, we want to study, we want to carry out a careful analysis of the residual stress in the region of the notch. So we perform 3 types of residual stress measurements. The first one is a conventional X-ray analysis. By this analysis can be performed away from the notch, and we can determine the residual stress profile from the surface to below the surface. The compressive peak in this case is around 50 micron below the surface, and the compressive layer is nearly 50 micron. The other measurements were taken in the region of the notch, and for this reason we used 2 different techniques: a micro XRD diffractometric analysis, and with this analysis we can observe that the residual stress due to the speed increased moving toward the notch. Increase moving toward the notch, and the notch severity increase also the stress concentration. So there is a stress concentration effect due to the geometrical details. The region that is affected by the notch geometry in this case is nearly 0.25 millimeters. Similar results can be obtained also with another technique, SEM FIDAC technique. In this case, we analyze with digital image correlation the effect of micro holes or macro slots that are carried out in the region of the notch. And also in this case, we can find a similar trend in terms of notch severity and stress concentration factor. So we have information now about the residual stress field, and we try to rebuild, to reconstruct this residual stress field in the whole specimen by using a finite element analysis. In order to do that, we can use a superposition of fictitious thermal fields, introduction of thermal eigenstrength, and in particular, in order to take account of the residual stress far from the notch, we can use a temperature distribution similar to the residual stress profile that we have measured in experimentally measured. In the region of the notch edge, we consider another function, a superposition of another temperature field, which decay going away from the notch. We have also to fit this function by performing a finite element analysis by determining the inverse coefficient of unitary temperature applied in any node of our finite element. By this information, we can determine the coefficient of our fitting function by using the normal equation. Moreover, in order to take account also of the uncertainty in experimental measure, we carried out also a Monte Carlo simulation by considering population of residual stress data randomly generated on the basis of the Gaussian probability density function of the experimental measures. In this way, we can fit the experimental measurement here. In the following slides, we can observe the fitting. It's a very good agreement with experimental results. And in the left down corner, also the residual stress field on the notch bisector for this specimen. This is for the blunt notch. Similar results can be found also for the sharp notch and for the very sharp. which we can observe the evolution of the residual stress in the region of the notch head. And so this can have a very important effect on fatigue because notch influences the effect or residual of short peening of the treatment. In order to complete our analysis, we perform a fatigue test campaign on this specimen by carrying out a 4-point pulsating bending test on a microtron Rumor resonant machine, exploring a fatigue life between 100,000 and 100 million cycles. And results of this analysis are reported in these two cards. Here on the top, the material as residual, not peened, and in the bottom, the peened results. We can observe very interesting results for a smooth specimen, not notch specimen, and blunt notches. The highest improvement can be found in the medium regime, life regime, between 500,000 and 5 million cycles, whereas the highest improvement for sharp notches is obtained in the very high fatigue cycle regime, in the region up to 100 million cycles. So a difference between the two notch geometries. Now, another important observation that we can try from the experimental results is that the fatigue notch sensitivity for the peened variant is reduced for all the notches, but in particular for the blunt notch. Moreover, the notch sensitivity factor is nearly sensitive to the notch root radius. For the unpeened variant, for the civil material, the evolution fits quite well the Peterson equation. With this information and the information of about the residual stress, we try to simulate the fatigue behavior of this material. And as did in the previous research, we tried to use a multi-axial fatigue criteria, cross-normal fatigue criteria, incorporating residual stress in the mean component of stress. And we use also the critical distance method, an area method, to account for the stress gradient at notch. Alpha C and beta C are material parameters previously determined. The critical length has been estimated using the LADAT distance. This is strictly acceptable only for very long fatigue life. The results of this simulation, we compare here the experimental results, point the symbols, and the simulation, taking account the effect of residual stress into a fatigue, multi-axial fatigue design. What we can observe from this analysis, there is an accurate estimation of the fatigue behavior for blunt notches and also partly for the sharp notch. Whereas we can observe that for the very sharp notch, we are not able to predict the change in slope, the knee point for the car, and also we have an underestimation of the fatigue life at very long, of the fatigue strength, sorry, in the very long fatigue life. The first aspect can be probably explained by the fact that we use a critical length that is not correct for the short fatigue life. In the literature, it's suggested to use different critical length to simulate the results for medium short fatigue life. In the second part, probably, we are not able to account for a phenomenon of track arrest due to the very sharp, very steep gradients of stress that we have introduced into the notch root is that we have seen in the reproduction of the residual stress profile. So I come to the conclusion. We have the main results of this research are that we have tried to measure the residual stress field in the vicinity of the notch. We have found that there is a correlation between the notch geometry and the residual stress field that is produced by the shot peening treatment. We can reproduce numerically this residual stress field by a superposition of thermal eigenstrength, and the results of residual stress can be incorporated into a multi-axial fatigue criterion, and with this criterion we can correctly predict specimen with blunt notch, but not the very sharp notch. In this case, we have to go on with our research in order to understand the difference that we have found in our analysis. Thank you for your attention.